Hi everyone, I'm Mr. Fullerton, and today I want to talk about electric potential difference. Our goals are going to be to define and calculate electric potential energy and to define and calculate electric potential difference. Then, to round out our discussion, we'll utilize electron volts as a unit of energy when we're dealing with very small charges moving through a potential difference. So why don't we dive right in? When you move a charge in an electric field, you have to do work. You apply a force through some amount of distance or displacement. A force over a displacement is work. And if you do work on something, you give it energy. So in this case, this would be electric potential energy. We use the symbol capital W quite often for electric potential energy. We also use that for work. So the work done on an object is the electric potential energy you give it. Or if it has electric potential energy and it does work, the amount of work it does gets subtracted from its electric potential energy. The work done per unit charge in moving a charge between these 2 points in an electric field is known as the electric potential difference, and we give that the symbol capital V. The units of electric potential difference are probably familiar to you. We know those as volts. So 1 volt is equal to 1 joule per coulomb of charge. We can relate these using the formula capital V for electric potential difference is the work done, or the electric potential energy, divided by the charge in coulombs. So, let's take a look here. If we wanted to apply this, a potential difference of 10 volts exists between 2 points A and B within an electric field. What is the magnitude of the charge that requires 2 times 10 to the minus 2 joules of work to move it from A and B? Well, I'm going to start by writing what I'm given. Potential difference of 10 volts, so V is 10 volts. What is the magnitude of charge that requires 2 times 10 to the minus 2 joules of work? So W, our work, is 2 times 10 to the minus 2 joules, and we're looking for charge. We can use our relationship, V equals W over Q. Now we solve for the charge. Charge then must be work over voltage. I substitute in with units. 2 times 10 to the minus 2 joules over 10 volts gives me a charge of 2 times 10 to the minus 3 coulombs. Let's take a look at another one, this time solving for the work or energy. How much electrical energy is required to move a 4 microcoulomb charge through a potential difference of 36 volts? Well, we're looking for electrical energy. We know our charge is 4 microcoulombs, or 4 times 10 to the minus 6 coulombs, and our potential difference is 36 volts. We can use the same relationship again, V equals W over Q, this time solving for W. W must be QV, which will be 4 times 10 to the minus 6 coulombs times our voltage of 36 volts. Multiply those together, 4 times 10 to the minus 6 times 36, and I get 1.44 times 10 to the minus 4 joules. All right, why don't we try yet another one? This time let's solve for the electric potential difference. If 1 joule of work, W equals 1 joule, is required to move 1 coulomb of charge, so Q equals 1 coulomb, between 2 points in an electric field. Find the potential difference. All right, our relationship, potential difference, is work or energy over charge. That's going to be 1 joule over 1 coulomb, or the definition of 1 volt. All right. One last one where we'll solve for electric potential difference here. In an electric field, 0.9 joules of work is required to bring 0.45 coulombs of charge from point A to point B. What is the electric potential difference between points A and B? Well, same relationship, V equals W over Q, or 0.9 joules over 0.45 coulombs. 0.9 over 0.45 will give me 2, and 1 joule per coulomb is the definition of a volt. So 2 volts here.